Scientists just found a planet orbiting exactly where every formation model says nothing should survive. In 2020, astronomers confirmed a Jupiter-sized world circling the white dwarf WD 1856 plus 534 every 34 hours, a star that violently swelled and should have swallowed it. Then came Halla, a giant orbiting a dying star that erupted past the planet's orbit, and PSR B1257 plus 12, worlds around a spinning stellar corpse. Each defies the rules. So how does a planet outlive the death of its own sun? That question cuts against everything textbooks teach about how worlds are built. The standard picture, called the core accretion model, needs a calm, stable disk of gas and dust around a young star. Grains stick together, grow into pebbles, then rocks, then cores massive enough to grab gas. The theory, refined heavily by Japanese astrophysicist Hidenori Ide and American Peter Bodenheimer through the late 1970s and 1980s, holds that a core must reach roughly 10 Earth masses before runaway gas capture begins. Models put that timeline at anywhere from 1 to 10 million years, and the surrounding disk typically disperses within about 3 to 5 million years, blown away by stellar radiation. That leaves a punishingly narrow window. It is slow, patient chemistry on a cosmic scale, and it insists on order. Yet the sky keeps breaking that order. When we actually count the planets, the tidy story cracks. By 2024, astronomers had confirmed over 5,800 exoplanets, and a stubborn fraction sit in places the model calls lethal. The first of them arrived in 1995 when Michel Mayor and Didier Queloz announced 51 Pegasi b, a gas giant orbiting its sun-like star every 4.2 days. That single detection, which later earned them a share of the 2019 Nobel Prize in Physics, forced the field to confront a class of planets the theory had never predicted. Take the hot Jupiters. These are gas giants roasting closer to their stars than Mercury's orbit of 0.39 astronomical units from our sun. Their daytime temperatures can climb past 2,000 degrees Celsius, hot enough to vaporize iron and rain it back as metallic droplets on the night side. They should not be there. And yet, again and again, there they are, making up roughly 1% of the stars we survey. The reason their location is so offensive to theory comes down to temperature. Gas giants need cold. They form far out in a disk, past the frost line, where ices survive and pile onto a growing core fast enough to hoard hydrogen and helium before the gas disperses. In our own system, that frost line sits near 3 astronomical units, just beyond the asteroid belt, at a temperature around 150 Kelvin where water freezes solid. That is why Jupiter sits at 5.2 astronomical units from the Sun. It was born in the deep freeze, and it carries more than 318 Earth masses of material it could only have gathered in that cold reservoir. So a giant whipping around its star in less than a day is a chemical impossibility built in the wrong neighborhood. There are only 2 ways to resolve that impossibility. Either the planet formed far out and moved inward, or it survived a place that should have destroyed it. Migration and survival became the twin escape hatches for the whole field. Migration itself was first modeled seriously by Peter Goldrake and Scott Tremaine in 1980, who showed that a young planet exchanging angular momentum with its disk could spiral inward in as little as 100,000 years, fast enough to threaten falling into the star entirely. And no object tests them harder than the first world we mentioned, orbiting a dead star. WD 1856 plus 534b earned its place in history in a single stroke. Discovered by NASA's TESS mission and confirmed in 2020 by a team led by Andrew Vanderberg of the University of Wisconsin-Madison, it became the first intact giant planet ever found transiting a white dwarf. Every 34 hours, it crosses the face of its star and dims the light. Because the white dwarf is so tiny, the transit is unusually deep, blocking well over half the visible starlight, and the whole event lasts only about 8 minutes. But this star is not like our sun. It is a white dwarf, roughly 40% of the sun's mass crushed into a body about the size of Earth, a star's worth of matter squeezed into a planet-sized sphere. It lies about 80 light-years away in the constellation Draco, and its surface has cooled to roughly 5,000 Kelvin over the estimated 6 billion years since it died. And here's where the trouble truly begins. To orbit that close today, this planet had to live through the most violent chapter of its star's life. Billions of years ago, before it collapsed into a white dwarf, that star was a red giant. It swelled outward, bloating monstrously. Red giants can balloon past 1 full astronomical unit, far beyond where this planet now sits, at only about 0.02 astronomical units. Our own sun, in about 5 billion years, is expected to expand to roughly 200 times its present radius, engulfing Mercury, Venus, and quite possibly Earth in the process. WD 1856 plus 534b sits at only about 3% the distance where such a swelling star's surface would have reached. If the planet had been in its current orbit back then, it would have been swallowed whole and vaporized. So it could not have been there during the swelling. That single deduction reshapes the entire story. The planet did not survive in place. It arrived afterward, migrating inward long after the star had died and shrunk. The question then becomes mechanical. What could drag a giant planet thousands of times closer to a burnt-out star? Astronomers have floated several culprits, none of them gentle. One is common envelope evolution, where the dying star's outer layers engulf a companion and fling gas and other planets outward. Vanderberg's team noted that WD 856 plus 534 sits in a triple system, sharing space with a pair of red dwarfs known as G229, 20A and B, about 1,500 astronomical units away. A possible engine for the Kozai leadoff mechanism, in which distant companions pump a planet's orbit into extreme ellipticals over millions of years. Another is gravitational scattering, where a second unseen body slingshots the planet inward on a wild, plunging orbit. Once it is close, tidal forces take over, slowly circularizing and shrinking that orbit over vast stretches of time until the planet settles into a tight, stable path around a corpse. A planet delivered, not born, to its impossible home. If WD 1856 plus 534b bends the rules, the next world seems to shatter them. Its name is Halla, and it should not exist at all. Halla is a giant weighing about 8 times the mass of Jupiter, cataloged formally as Baidu b and 8 Ursae Minoris b. Its discovery reached the wider world through a 2023 study in the journal Nature, led by Mark Hahn of the University of Hawaii. Using radial velocity data gathered over more than a decade at the Keck Observatory and confirmed by NASA's TESS. The star lies about 520 light-years away, and its name honors the mountains Baekdu and Halla on the Korean peninsula, chosen through an international naming campaign. The problem is brutal in its simplicity. Halla's host star expanded, during its own dying phase, right past the planet's orbit at 0.46 astronomical units. The star grew larger than the space the planet occupies. It should have been engulfed and destroyed. It was not. It is still there. So how do you save a world from being swallowed by the very star it orbits? The leading explanation is almost poetic. Perhaps the star never fully expanded to that lethal size because it was once not one star but two. If two stars merged, the collision could have halted the runaway swelling before it reached Halla, changing the whole timeline of the star's death. Hahn's team pointed to the star's unusual position on the color magnitude diagram, which is consistent with a helium-burning remnant of just such a merger between two smaller stars. In another version, Halla is a second-generation planet, born fresh from the debris thrown off during that merger. Today, the host is a red giant of roughly 1.7 solar masses. Either Halla dodged destruction, or it was reborn from the wreckage. Both answers are stranger than the puzzle. And still, these are not the most extreme survivors we know. For that, we have to visit the most hostile stellar remnant imaginable, a pulsar. A pulsar is a neutron star, the ultra-dense core left after a massive star explodes, and it spins at a speed that defies intuition. The pulsar PSR B1257 plus 12 rotates about 161 times every second, sweeping beams of radiation across space like a lighthouse gone insane. A single teaspoon of its material would weigh billions of tons, and its entire mass, about 1.4 times the Sun's, is compressed into a sphere barely 20 kilometers across. And it has planets. Those worlds carry a distinction that ought to stop anyone cold. Found in 1992 by astronomers Alexander Wolshan and Dale Frail using the giant 300-meter Arecibo dish in Puerto Rico, they were the first confirmed exoplanets ever discovered, found around a spinning corpse years before anyone confirmed a planet around a normal sun-like star. Wolshan detected them not by light but by timing. The pulsar's beats arrived microseconds early or late, betrayed by the tiny gravitational tug of orbiting bodies. The very first planets we ever detected beyond our system were orbiting the ashes of a dead one. That fact alone rewrites the intuition that planets belong to living stars. Yet a pulsar is born in a supernova, the most destructive event a solar system can face. No planet already in orbit could plausibly survive that blast, which means these worlds are not survivors at all. They are children of the aftermath. 3 planets circle PSR B1257 plus 12 with masses near 0.02, 4.3, and 3.9 times that of Earth, about 2,300 light-years away. They orbit at 0.19, 0.36, and 0.46 astronomical units, completing their years in roughly 25, 66, and 98 days, and the 2 outer worlds sit close enough to gravitationally perturb one another. An interaction Wolshan measured directly in 2003 to prove the planets were real. The best explanation is that they condensed from a fallback debris disk, material that failed to escape the explosion, settled back around the neutron star, and formed brand new worlds in the ruins. Put these 3 cases side by side and they demand something uncomfortable. A giant delivered to a white dwarf. A giant spared or reborn at a red giant. Small worlds forged after a supernova. Migration, scattering, and second-generation formation are all invoked, and no single model explains all 3. What unites them is not a mechanism but a moment. Each one survived or emerged from the death of a star. So we face a genuine fork. Either our formation models are simply broken, or planets are far more resilient and mobile than we ever assumed. The evidence leans hard toward the second answer. These are not violations of physics. They are physics operating over scales and situations we rarely stop to imagine. Once you accept that, the whole picture loosens. Planets do not form and then sit politely in place for eternity. Disk migration can carry a young world thousands of astronomical units across its system. Tidal capture can seize a passing planet and grind its orbit down over billions of years into something tight and stable. And debris disks, whether from a supernova or a stellar merger, can seed entirely new planets around stars that are already dead. In fact, in 2006, the Spitzer Space Telescope imaged exactly such a dusty disk around the young pulsar 4U0142 plus 61, direct evidence that the raw material for second-generation worlds really does gather around stellar corpses. Worlds wander. They get captured. And sometimes they rebuild after catastrophe. This is why the anomalies matter so much. They are not embarrassments to be explained away. They are signposts pointing at processes we are only beginning to map, and our tools are finally catching up. The James Webb Space Telescope can now probe the environments around white dwarfs and pulsars in detail once unthinkable. The upcoming Roman Space Telescope, targeted for launch by 2027, will hunt through the galaxy using gravitational microlensing and is expected to find thousands more planets, including the strange and the displaced. Its wide-field survey alone is projected to catalog around 1,400 microlensing planets, many of them rogue worlds drifting free of any star. Every anomaly, once studied, refines formation theory rather than destroying it. And that reframes the question we started with. A planet orbiting where none should exist is not a hole in our knowledge. It is a window into how common survival and rebirth truly are. The Milky Way likely holds over 100 billion planets. We have found them around nearly every kind of star, and now around the burnt remnants of stars too. Even a corpse can hold a world in its grip. Planets survive WH ear, PHY6, SAID, M possible. The lethal zones were never truly empty. They were simply waiting for us to understand how something could endure them. The universe does not stop making worlds when a star dies. It just changes the rules and keeps going. If stories from the edge of what we thought possible move you the way they move us, consider subscribing so you never miss the next one.